These 8 summits are incredibly important. We're addressing in each of them the intersection of a methodological question, a thematic question. Both of them are unavoidable. The first session was really how we work collectively now, what it means to be collective in a moment that we're acknowledging that the collective is not only people or our people, is not the we, but rather others that are not necessarily human, what it means that, and we were intersecting that with community engagement. So basically we're looking at cases of community engagement through the perspective of a methodological question is how our fields work collectively now. The second was about the how to speed up our action or impact actually in facing urgent crisis. That was the methodological question. Of course, we're very much relying on we will do something amazing and things will happen, right? But there's a kind of calendar for many things that we have to deal with. Sometimes actually times that we don't control, small or kind of short and fast, or they're super slow. But how we speed up is a big question. The third one was how we connect AI, local AI, with local intelligence, right? Local, and that was actually a journey that Laura Kurgan curated that took us to the school, but also looking at through the perspective of different practices within a school and the university to the way AI it's being understood as something that is challenged and interconnected and interdependent with other forms of knowledge and intelligence. This one, it's really a key question. It's about scaling up. How do we move things from one scale to the other is a crucial part of our disciplines. But how do we scale up is also crucial, and it's challenged the notion of laboratories and how we operate socially, but also it's an urgency. We have people here that have formulated this from an academic point of view, like Albena Janeva, working on what it takes to move things across scales, and David Benjamin opening the question of scaling up. David actually has been co-curating this session, but we will do that looking at something very specific, which is the case of carbon sequestration, something that is controversial, that is difficult, that is mobilizing scientific knowledge, engineering, but also big, let's say, societal and environmental change. And that's something that requires action and that basically allows us to discuss what it means to make things something to emerge as real. And that's what we're doing here. So the session, as you know, it's bringing people that are looking at these topics from different perspectives, and they have a different knowledge on that. And everyone that is in the center is crucial. We don't make distinction between those that are presenting and those that are in the auditorium. So I really encourage you to take notes and make sure that you contribute to the final Q&A and discussion. But now I want to pass it to Bart-Jan Polman, who's curating these sessions, to introduce the speakers. Thank you.
Thanks, Andres. Good evening and welcome all of you to the 4th Actioning Summit. So far, we've discussed working collectively, affordable housing and AI, and tonight we move on to something that at first sight might appear quite different, but what I would argue is closely related. As many of you, as you may know, what is aimed at with this Actioning Summit is to discuss the how, the specific methodologies and specific knowledge used by experts on these topics that led to tangible or might lead to tangible real outcomes. And tonight we will discuss the methodological questions around scaling up, how to scale up, as was just explained, and in this particular case as it relates to carbon sequestration. So a warm welcome to all of you, and especially to our speakers tonight, GSEP's own David Benjamin, Timothy Bushman of Carbon Removal Canada, Mehrdad Mahouchian and Yuri Mitko of Carbicrete, Aidan Sader of Carbon Capture, and of course Albena Janeva of GSEP Princeton and Politecnico di Torino. And welcome also to our interlocutors, Lola Benalon, who's sitting there in the middle, Michael Bell and Philip Braam, and as always to the many people watching online. So my name is Bart-Jan Polman. I'm the Director of Exhibitions and Public Programming here at GSEP. And by means of an introduction to tonight's topic, I want to highlight 4 events, all within the span of only a few days or hours even, to somewhat contextualize also what we are discussing. The historic droughts we've witnessed in the Northeast and the resulting wildfires and smoke all of us here in New York were breathing up until yesterday. The outcome of the elections and the uncertainty this brings to many things, including US climate policy. COP29, whose opening date this summit sort of perfectly aligns with, started today, earlier in Baku, Azerbaijan, a petro-state, and perhaps least known, the fact that several hours from now, judges in the Netherlands will release a highly anticipated verdict in a major court case between an environmental organization and Shell Oil that might have significant impacts on Shell's operations. If all this shows both the urgency and the possible ways in which the climate crisis might or might not be addressed, then we can certainly debate here what is the best way to do it and who is responsible for what. I also want to take one step back and address the very methodological question of scaling up that is central tonight, which we may well apply to other fields as well, and to highlight what is needed to tackle the real sort of immensity of this issue at the sort of planetary scale. So the question, as I'm sure we'll see with a company like Carbicrete, for example, is then how to get from the scale of the laboratory, please welcome all of you, to the scale of the planet, and we will discuss carbon sequestration tonight broadly from sort of four perspectives: materiality, direct air capturing, policy, and academia. So just a few words about how the evening will unfold. We will first hear from our speakers. Each will speak for about 10 minutes. And then after the 5 presentations, we will hear targeted questions from our respondents, and I will then open it up to all of you. Because we have many speakers, we will try to keep a strict control of the time, and I want to introduce Lane, who's sitting there in the front, who has a flag. Can you show the flag? Flag? Yeah. That's the flag that will go up. Lane. Oh. Lane. Can you show the flag? Yeah. So we have a flag here that after 10 minutes will go up, and that means that your time is up. And I also will keep my introductions very short, way shorter than they deserve. But all of the biographies are online, so please no offense. We'll start with David Benjamin, founding principal of The Living and associate professor at Columbia GSEP, whose incredible work has been included in many exhibitions and collections, including MoMA. And I also want to mention here, which was already said, that David has been incredibly helpful in sort of putting this session together, and the topic was really conceived together. So after David, we will hear from Mehrdad, the Chief Technology Officer and co-founder of Carbicrete, and Yuri Mitko, Carbicrete's Chief Marketing Officer. And Carbicrete's technology, first developed at McGill University, uses slag from steel factories to replace cement in concrete products. And this project injects CO2 into concrete to provide strength, while permanently sequestering CO2 within its products. We will then hear from the world of DAC, direct air capturing from Carbon Capture's VP of Corporate Development, Aidan Sader, who has experience both in the world of finance and as an engineer on large-scale energy projects. Timothy Bushman, who is a Columbia graduate, is the Director of Policy and Research for Carbon Removal Canada, an independent policy initiative focused on the rapid plus responsible scale-up of carbon removal solutions needed to meet Canada's climate goals. And I want to highlight something from their website, which states that carbon removal is an essential tool in the clean energy transition and must be used in addition to and not in place of reducing emissions. And Albene Janeva, lastly, is a sociologist and architectural theorist whose research across the boundaries of science studies, architectural theory, cognitive anthropology, and political philosophy spans all those fields. And she's a full professor at the Politecnico di Torino in Italy and teaches here at Columbia GSEP and at Princeton. Then our interlocutors, Michael Bell, professor of architecture here at GSEP and of course of Bell's Young Architects, Lola Ben-Alon, who directs the Natural Material Labs here at the school and is an assistant professor, and of course Philip Rahm, who needs little introduction and who is an expert on climate, teaches here as well, and is of course the principal of Philip Rahm Architects. So with that, the summit is officially open, and I hand the floor to David.
Thank you very much, Andres. Thank you, Bart. And it's great to be here. And I'll just launch right in with some quick thoughts about this topic of carbon removal architecture. So I'm sure we all know already that the climate emergency is in large part an emergency of carbon pollution. And at the risk of oversimplifying, I'd like to outline this kind of climate and carbon framework that I think will set the stage for the discussion tonight. This is also a framework that informs the new subfield of carbon dioxide removal. Many of the speakers part of that subfield. And it's a framework that's influenced a shift in some of my own work on sustainability and the built environment. So this framework is guided by the world's best climate scientists and the United Nations Intergovernmental Panel on Climate Change, and it's been summarized by academics and people like Nan Ransohoff from an organization called Frontier Climate, which I'll describe a little bit later. And the basic idea is that in order to avoid the most devastating and irreversible effects of climate change, we should limit global temperature rise to 1.5 degrees above pre-industrial levels. And this translates to reducing global annual carbon emissions from about 50 gigatons to 0 by 2050. And there are two main levers that we can pull to get there. Lever 1 is to reduce, and lever 2 is to remove. So for reducing carbon, this means emitting less carbon dioxide into the air from all the things we do. And this is shown on the graph here. Oops. Didn't advance. This is shown on the graph here in the gray shape. So you can see this rapid reduction that's necessary. And for removing carbon, this means actually taking carbon dioxide that's already in the air out of the air. And this is shown by the brown shape. So most of the efforts on the carbon problem to date have been on reduction, lever 1. And this is because it's the lever that we can pull the fastest and with most dramatic effects. But it's now generally recognized that reduction alone will not solve the problem. For one thing, some emissions will be very hard to decarbonize, such as making jet fuel and making concrete. And these emissions make up about 20% of the total carbon. These hard-to-abate emissions are 20%. But for another thing, the concentration of carbon dioxide in the air is already too high. So even if we reduced emissions to 0 tomorrow, we would still need to take carbon out. And these charts basically show how dire the situation is, with 2023 and 2024 shown in blue and red, and they're literally off the charts in terms of highs and lows. We're in new territory here. So lever 1 is incredibly important, reducing, and architecture has a huge role to play. Here's a diagram by Saul Griffith of all the energy flows in the United States, which can be used to do things like find some of the most important strategies for reduction and their scale. But the focus of the discussion tonight is on lever 2, removing carbon dioxide from the air. So in terms of numbers, we need to basically decrease emissions from 50 gigatons per year to 10 gigatons per year by 2050. And at the same time, we need to increase carbon removal from 0 gigatons basically to 10 gigatons per year. And to give a sense of scale, this dark brown box represents about 4 gigatons, which is a very low conservative estimate of the amount of carbon we need to remove per year. And this tiny orange pixel, which needs to be magnified to even see it, represents about 10,000 tons, which is all of the carbon dioxide removal achieved to date. So the point is that we have a carbon problem and also a scaling up problem. And the question is, how can we go from this orange pixel to this brown box in the next 25 years? And this brings us to the world of carbon dioxide removal. So the term carbon dioxide removal refers to both natural and mechanical processes that result in less carbon in the atmosphere than before the process was run. There are a couple of quick caveats here. Basically, oceans and soil are natural carbon sinks, but they're not generally included in the category of carbon removal because they're a baseline and they're not additional removal. And then also for reference, carbon removal is generally understood to be distinct from carbon capture. And carbon capture is things like trapping and storing carbon that comes from carbon-emitting processes like coal-fired power plants. So basically, carbon capture does not actually reduce net carbon. So one example of carbon removal approach is something called direct air capture, which involves creating machines with big fans that suck in air and use filters and chemical reactions to remove carbon dioxide. Then the carbon can be dissolved in water and injected underground into things like basalt formations, where it fuses into rock and becomes trapped for thousands of years. Another approach is called enhanced weathering, which involves starting with rocks that already naturally absorb carbon and speeding up this process through crushing rocks into fine sand to increase their surface area. Another approach is seaweed cultivation, which involves growing kelp that absorbs carbon as it grows, and then sinking it to the bottom of the deep ocean where it will remain inert, trapping the carbon for thousands of years. And yet another approach is called biomass burial, which involves taking plants or agricultural waste and basically sealing it or burying it in a way that it won't be able to biodegrade. This is sometimes called carbon casting. So the world of carbon dioxide removal is forming around a loose coalition of academics, scientists, government agencies, startups, and corporations with ambitious climate commitments. And they're all aiming to kind of jumpstart this new industry. It's moving pretty fast. It's gaining a lot of attention, as you can see here in this recent front page article in the Times. But carbon removal is controversial for a few reasons. First, much of the technology of carbon removal is unproven and hasn't yet been demonstrated at scale. Second, the natural and mechanical processes of carbon removal often or sometimes involve large amounts of land, water, and energy, so we have to be careful about that. And third, and maybe most importantly, investing in carbon removal may result in less immediate action to reduce the amount of carbon being emitted in the first place. It may offer an excuse to continue business as usual. And this is a photo of executives from Occidental Petroleum breaking ground on a large carbon removal project in Texas, which they plan to use as an excuse to keep extracting and burning oil. Nevertheless, the UN IPCC and many others believe that since the world has failed to address the climate emergency so far, and since the level of carbon in the atmosphere is already so high, we must now pursue carbon removal with urgency. It's too late to go the ideal route. So one question is whether or not we should pursue carbon removal, but then another question is, if we do pursue it, how should we do so? What's the plan, especially given the scale of 10 gigatons per year and the timeline of 25 years to get there? In 2021, an organization called Frontier Climate was formed with the idea of accelerating this new field of carbon dioxide removal. Frontier raised about $1 billion of private investment, and they were guided by the concept of what's called an advanced market commitment, which is basically a mechanism that allows us to buy products from the future in order to support their development today. It gives people an incentive to invent and develop these products that don't yet exist, and it's a signal to innovators, if you can build it, we will buy it. So advanced market commitments have worked before, in particular with the development of vaccines. In 2007, a group of governments and philanthropists set out to accelerate the development of the pneumococcal vaccine in order to prevent one of the most common causes of death for children in poor countries. And the idea was to basically guarantee enough future demand, about $2 billion worth of purchasing, in order to encourage suppliers, which were the pharmaceutical companies, to build something that should exist but doesn't already exist. And basically it worked. So within 4 years, a successful vaccine was developed. Hundreds of millions of doses were purchased and distributed, and about 700,000 lives were saved. So the idea here is that the same advanced market commitment mechanism that worked for a vaccine might also work for carbon removal. 2 years after Frontier launched, Microsoft pledged about $1 billion of its own funding to accelerate carbon removal. The UN is currently working on standards for a carbon market, which may be announced in the next few weeks at COP29, which Bart mentioned. But meanwhile, Frontier, Microsoft, and the rest of the carbon removal field have created some criteria for evaluating potential carbon removal approaches and projects, including, oops, I see it's not showing here, but including environmental justice, basically empowering local communities and ensuring equitable distribution of benefits, but also harms. And also another key one is durability, meaning that the carbon is going to be locked away and out of the atmosphere for a very long time, often with a target of 1,000 years. So we have these criteria for what it means to do good carbon removal. But of course, the idea is that private investment is just the first step. It should be a bridge to a future where governments invest in CDR. And this is starting to happen now, but it's slow. Earlier this year, the bipartisan infrastructure law in the United States distributed an initial investment of about $1.2 billion to advance the development of commercial-scale carbon removal facilities in Texas and Louisiana. This is a rendering of the plan for Louisiana. But again, the issue of scale is daunting. So we need to reach about 10 gigatons per year by 2050, and public and private leaders have generally acknowledged that we should aim to reduce the cost of carbon removal to about $100 a ton. And this means, in terms of scale, that the world will need to spend about $1 trillion every year on carbon removal, starting in about 25 years. So that's a huge amount. How can we get our heads around these numbers and make a plan for this? Nan Ransohoff, who I mentioned earlier, and who's the head of climate at Stripe and also leads Frontier, has an interesting idea that maybe we could compare government investment in carbon removal to government investment in development aid. And the UN already has this long-standing target for developed countries to spend about 0.7% of gross national income every year on development aid, although recently countries have not been hitting that target. But if development countries created a new target or an additional target to spend about 0.7% of gross national income on carbon removal, in addition to spending the same amount on development aid, basically this could work. So it's showing that it's not impossible. This would provide about $100 trillion in total investment by 2100, which is about the investment required to stabilize the climate, in addition to the drastic reductions that are needed and that people are already working on. So we may debate some of the assumptions here, but I'm just saying this to point out that this is the kind of thinking about scale that the topic of carbon requires. So with this general framework in mind and this background about a newly forming industry, what is the architecture of carbon removal? So it's well known that buildings contribute about 40% of global carbon emissions. So buildings can play a huge role in lever one, reducing carbon. And as a discipline, we've outlined how this can be broken down into these kind of two pillars, we could call them, of operational carbon and embodied carbon. But in addition, we may want to start thinking about a third pillar of carbon removal. In other words, architecture and buildings might be relevant to carbon removal in two ways. First, architecture might incorporate carbon removal into individual projects. I'll talk about that in a second. And second, architectural intelligence and design might be necessary to create this new industry of carbon dioxide removal. So more specifically, carbon removal architecture involves things like factories, like the one shown here, that suck carbon out of the air. Or it might involve massive direct air capture facilities, like this rendering shown here. Or buildings and cities made of carbon storing material, like timber. Or this example, closer to home, of a New York City building that's already meeting its local law 97 requirement to reduce emissions by capturing them from its mechanical systems in the basement, basically, and then injecting them into concrete at a local cement plant. They basically have this mechanism to take the concrete from the equipment, pipe it into a truck, drive that truck to Queens, and then put that carbon into building materials. This is a project called Timber City, kind of an academic project, but it is exploring how mass timber could scale up and lock in carbon in hundreds of thousands of buildings throughout the city. Here's some of the work of my own studio for a confidential client at the moment on the design of some direct air capture equipment and buildings. This is a carbon negative facade system that we're developing in my studio along with several collaborators. And the idea here is to take a biomaterial made of mycelium, which stores carbon, and it's made of mycelium and agricultural waste, and then cover it with a thin shell of fiber reinforced polymer in order to lock in that carbon in a building facade that can be installed today. So we think of this as a kind of drop-in technology because it can be dropped into today's systems that are already running. It's the most radical thing that's possible right now. It can be used with today's building codes and construction practices on today's buildings, and we're installing it on a 300-unit affordable housing project in Oakland, California. This kind of drop-in technology may require some compromises. It's not the ideal entirely biogenic architecture of the future, but it's the kind of compromise, and this is the kind of topic that carbon removal architecture kind of raises. What do we need to get there given the scale of the problem and the timeline of the problem? So we're also working on the architecture of carbon removal at GSAP. And you can see some of the models from students in a studio this semester at the back of the room, and some images of things they've been working on. And here's some work from some of my current and previous students at GSAP. This shown here is an exploration of a temporary community and laboratory constructed with materials made of sugar. Here's a factory on agricultural land that's aiming to take rice straw and turn it into construction materials. Here's some physical prototypes of adding biochar to concrete as a way of storing carbon that has been removed from the air. This is an exploration of storing carbon in blocks. And if materials can be carbon negative, then maybe this inverts our usual expectations of architecture. Maybe instead of walls and columns being thin, maybe they should be as thick as possible. Maybe buildings become places to keep carbon locked away, as well as places to shelter humans. Here's a web-based analytical tool that explores sourcing and utilization of mass timber across the world, including the necessary connections in order to scale up. This is a town hall converted into an urban farm and mass timber factory, which hosts community events in evenings and on weekends. The architecture of carbon removal may be technological, but it may also be organic. It may be infrastructural, but it may be decentralized. It may be empowering, and it may be collective. And in any case, it will be urgent, and it will be vast. So our new carbon removal buildings and cities will need to be designed and constructed at a massive scale, navigating the complexities of technologies, environmental justice, land use, jobs, society, and many uncertainties. And there are many important questions to consider. For the DAC approach, direct air capture, will we need 10,000 plants the size of the largest plant constructed to date? Should we create large arrays of machines in the landscape, like the fields of photovoltaics in Spain or California? Do we have enough land and water and renewable energy? Or should we create construction materials made of plant-based material that will lock in carbon? How will we make sure the carbon remains locked in for 1,000 years? What about the oceans? Should we convert expanses of ocean to farm algae and sink it to the bottom of the sea? How will we monitor this approach and ensure that the carbon does not escape back into the atmosphere? More generally, how do we design the project and also the necessary scaling up? How do we design new flows of carbon, and how do we draw them? And who will control this architecture of carbon removal? Who will design it? Where will it be located? What kind of world will it envision? How will natural and mechanical systems be balanced? How will jobs and public services be managed alongside the management of carbon? And finally, the system of carbon dioxide removal is interconnected with many other systems, systems of energy, systems of water, systems of geology, labor, natural ecosystems, economics, and policy. We can't plan this and we can't design this in isolation. We need to think about systems design. We need to consider potential risks and also design potential co-benefits. And this is another way that architecture and architectural intelligence can be relevant. Yet it's also important to note that while we can draw on a range of architectural skills, we may have to develop new skills. We may have to develop the capacity to simultaneously design a project and design the capacity to scale up. We may have to develop the ability to work with massive numbers beyond our usual intuition. And we may have to change the way we teach architecture and even the way we conceptualize it. And it's with this in mind that I'm excited to hear from our other speakers and to start this important discussion at GSAP. Thank you.
Thanks very much for having us. My name is Yuri Mitko. I'm the Chief Marketing Officer at Carbonecrete. This is my colleague Mirdad Mahushin, who's the Chief Technology Officer at Carbonecrete and also a co-founder of the company. We are a carbon removal technology company based in Montreal, Canada, and we have a patented process that enables the production of cement-free concrete. So what our technology does is it replaces 100% of the cement content in precast concrete, masonry, and hardscape products with steel slag, which is a byproduct of the steel making process. It's often landfilled, but it has the ability to act as a binder in concrete, much in the same way that cement does when it is activated with carbon dioxide. Carbicrete has been around since 2016. Since incorporation, we've grown to about 50 employees. We've raised just over $40 million from a pretty diverse group of investors, which include financial investors, but also some key strategic investors as well. I don't think I have to tell anyone here about the emissions problem that cement poses. Cement-related emissions account for about 8% of the world's greenhouse gas emissions. And the biggest reason that cement and concrete industries are considered to be amongst the hardest to abate is because there are very few viable substitutes for cement as a binder in concrete. There are a number of different pathways that can help reduce our reliance on cement as a binder, and ours is one of them. And I'm going to turn it over to Merdad, who's going to walk you through the technology and also talk about how the process actually plays out.
Thanks, Yuri. So what is the solution? The solution is to completely replace cement with a steel slag. What is a steel slag? A steel slag is a byproduct of steel manufacturing process. And you may say that use of a slag in cement or in concrete has been done in the past. What's new here? The new thing here is that in the past they were using slag as iron slag. So we talk about steel slag here. So there's a huge difference between a steel slag versus iron slag. So in our process, in our solution, 100% of cement is replaced with steel slag, and the steel slag is delivered to the concrete manufacturing plants. The rest of the equipments are going to be the same. So the manufacturer of concrete can use the same equipment, including the mold, the conveyor belts, silos, so on and so forth. So all of those standard equipment can be still used. Another change is the curing chamber, that we need a specific type of curing chamber in order to cure our block or our concrete product with CO2. So inside the curing chamber, CO2 gas is injected into the chamber. A chemical reaction happens between steel slag and CO2 gas. And in less than 24 hours, we are able to get to the right level of performance, so the blocks or the concrete products can be removed from the chamber. And in fact, after 24 hours of curing, the performance of our blocks is better compared to the commercial cement blocks or pavers. Regarding to the process and how the process works, so steel slags consists of lots of oxide, including silica oxide, iron oxide, and calcium oxide. For us, calcium oxide is very important because we talk about the mineralization here. Regarding to the mineralization process to happen, calcium needs to be leached in water. At the same time, CO2 that we are injecting into the system is going to be dissolved in water, generates bicarbonates. So the combination of these calcium ions and bicarbonates generates calcium carbonates or limestone. And these limestones, which are on the very small size, nano-size particles, are going to fortify the microstructure of the concrete, and it makes blocks and other concrete products strengths, basically. What are the main difference with the commercial concrete products versus us is the use of different binder. Concrete and cement, they have been around for the past 200 years. I think cement was first invented in 1824, almost 200 years ago. What's the properties of cement is a hydraulic material. It means that it can react with water, and basically it gains a strength due to a hydraulic reaction. The reaction of cement and water generates calcium silicate hydrates and calcium hydrides. And that's how cement works, basically. In contrast, as I mentioned, we are using a steel slag as the only binder in our concrete products. Steel slag has very limited hydraulic properties. So it means that if you mix it with water and just you leave it there, it gains a little bit of the strength, and that's it. It's not going to give you enough strength. So steel slag needs to be activated by CO2. The reaction happens between the steel slag, CO2, and calcium silicate hydrates and calcium carbonates are generated, which is very beneficial for us because CO2 can be permanently absorbed and sequestrated by slags. And in the ambient condition, in the atmospheric condition, that calcium carbonates are going to be stable. They are not going to go anywhere. So even if you crush the concrete, if you are crushing the paver, CO2 is going to be locked inside those concrete and is going to be stay there forever. And that process is called mineralization. So Yuri, back to you.
Yeah, so the main topic of discussion here is obviously carbon sequestration, but I thought it'd be worth maybe just taking a quick moment to look at some of the other environmental benefits that are associated with this process. So the most obvious is obviously emissions reductions that are associated with cement production. So we avoid 100% of those. Also, waste reduction. We're using a byproduct of the steel making process. It's often landfilled. And so that's another benefit is the reduction of landfill waste. And then maybe a little less obvious, but I think of particular interest to this group is the reduction of embodied carbon in the built environment. So it's one thing to take carbon dioxide and to store it away somewhere. It's another to put it into a valuable construction product that when you then use it, serves to reduce the embodied carbon of the building that it's being used in. So in terms of quantifying the carbon impact, if we just take it at a unit level, we'll take one of those blocks. That's a typical concrete masonry unit. It's about 18 kilograms. One 18-kilogram block represents about 1.5 kilograms of avoided emissions, and then anywhere between half a kilogram to a kilogram of carbon dioxide that's permanently removed during the curing process. So how does that scale? If we look on the right and take a concrete plant that produced sort of a mid-sized concrete plant producing about 10 million units a year, that's a big plant, but it's not a huge plant. You get about 20,000 tons of combined reductions and removals on an annual basis. And if you just extended that out to say 25 customers or 25 plants, you're starting to get into that kind of half a megaton scale. And just theoretically, if we were to take all the steel slag that is produced annually in the world and put it all into concrete, then we'd be looking at 250 million tons of combined reductions and removals on an annual basis. So in terms of our own approach to scaling, we're essentially a licensing company. We license our technology to concrete makers, which has the benefit of leveraging existing infrastructure. So the concrete plants exist, the equipment exists, the producers exist. Yes, we have to add curing chambers, but essentially all the infrastructure to make these products is existent. The distribution channels and sales channels, end users, all of those exist as well. And so that's one of the advantages of our licensing model is that we're leveraging all that existing infrastructure. In addition to the environmental benefits, this process, when implemented, offers our customers significant business value as well. Most importantly, and this is the main buying motive, is that it offers them a hedge against the rising price of cement. Cement prices are higher than they've ever been, and they're just consistently increasing. Whereas we're using as our feedstock a byproduct, an industrial byproduct that, as I mentioned, is a pretty low value. It has some applications, but relatively low use and low value applications. It also allows our customers to sell into the low carbon concrete market, so they can win jobs that require the use of low carbon products. We're also active on the voluntary carbon market, and so we share in the revenues derived from the sale of carbon credits with our customers. And then our customers also benefit from the fact that they've got in 24 hours full strength concrete that can be shipped and used at a construction site as soon as it comes out of the curing chamber, as opposed to a cement-based process where it takes a full 28 days before you get full strength concrete. Excuse me a second. In terms of where we are now and where we're headed, we've got a customer that is currently producing commercial products in Quebec. They're producing a variety of different products, and we're working with them to expand that product portfolio. We're also increasing capacity at that particular plant. In fact, there's equipment going in this week that's going to allow them to significantly increase their production output. We've got another customer coming online in Ontario in the beginning of 2025, which will allow us to sell into the Ontario market. We're exploring a few licensing opportunities in the US and also abroad. We've got a pilot project that we're running with Saint-Gobain, which is a large multinational French construction materials company that is an investor in Carbocrete. They have 14 concrete plants in France that we're hoping to have our technology deployed at in the coming years. And I mentioned that our core business is a licensing business. That's true, but at the same time, we are exploring a couple of singular opportunities to build a Carbocrete dedicated plant in the US. And sort of optimized scenario is to build a plant that is co-located or adjacent to a steel mill, and then also to have a source of CO2, like a DAC source, for example, or a DAC module on site, and then build a concrete plant with all those installations, fence to fence to fence. So I'll leave it there for that. Thank you very much.
Everyone's done a really good job of setting this up, and we are a vertically integrated DAC OEM, and I'll dive into what that means. But let's first level set again, what is direct air capture? Direct air capture acts as a vacuum. Why I say a vacuum? Because it removes the CO2 that has already been emitted in the air. This is a drastic difference than point source capture, which you would see avoiding the emissions released by industrial facility. This facility actually captures the CO2 that's already been emitted and then permanently either sequesters it in the ground underneath multiple layers of geology, or can go into various types of value-add products that we see here, concrete being one of them, and other pieces as well. Now, who are we? We are an OEM technology that's based out of Los Angeles, California. We've raised $90 million to date with shareholders, including the likes of Amazon, Siemens Financial. And our unique approach to this technology is what we call an open source modular system. We manufacture all of our own technology in our facility in Arizona, and it's modular. So think of a 40-foot shipping container, has our reactors within it. We manufacture it, you relocate it to site, and you have some support module systems. You put the Lego pieces outside, and now you have a DAC system. So when we think about scaling up, our unit scales and descales based on the location. One of the key benefits of this is the fact that achieving costs down and economies of scale is much easier done at the manufacturing plant than it is done at the engineering house. Large capital projects tend to have large capital overruns, whereby a lot of our cost is done within manufacturing, which we can control through the supply chain and pass that cost on to our clients and customers. And so what's the modular attribute of our technology? I think you saw some really nice fly-throughs or renderings of our competitor's facility. That was a Climeworks facility in Iceland. Our technology is similar, but it's a slightly different approach. And so although we still use the temperature vacuum swing adsorption process, what we've done is every piece of our technology is fully modular. So again, think of this module over here as a 40-foot shipping container relative size. Within each, there are a set number of DAC reactors. All the reactors are the same. They plug into these slots. Each one of these slots is the exact same. This becomes a module, and we relocate this to site. So as you see, this is the cartridge that actually captures the CO2. It goes into a reactor, which goes into a module, which goes into a facility. And as you can imagine, there's a really clean pathway of scaling this up. And so how do you capture the CO2? Air is brought into the DAC reactor system and is in contact with an amine-based sorbent. We have a proprietary sorbent technology. We have different generations that are in development in our materials science lab. Then there's some time given for the adsorption cycle. So the air contacts the sorbent, CO2 is removed and saturated within the sorbent itself. We then add steam to desorb the CO2. So now you have a pure CO2 stream of anywhere between 96% CO2, with the remainder being oxygen and nitrogen. And then you use vacuum pumps to suck that out and send it down for post-treatment. It's a very unique process in the fact that there's a lot of optimization that's going on. Today, there's really only about 30,000 tons per year of total deployment in service, of which, as of Q1 of next year, 2,500 tons is going to be ours. And so this was our Leo. This is not a rendering, by the way. This is our module. And so we first launched this earlier this year at the Port of Long Beach. And we've since relocated it to Phoenix, Arizona, where our manufacturing facility is. We are actively deploying our next generation of technology, which is going to be 2,000 tons. So there's going to be 5 of these units at site at our factory, where we've stacked 2 of these up on top of each other. These are load-bearing systems, so you can stack them as high as 3 up, which is going to be a unique approach when you think about how you design and for the locations that you design for. Now, how do you think about DAC in the built environment? We had heard about Frontier. We've engaged in offtake sales to folks like Frontier and Microsoft. We have over $25 million of offsets already sold. We're actively securing future offtake contracts. And so our approach to scale up has been very straightforward around, we first deployed 1 module, which was that 500 tons per year. Now we're deploying a cluster of 4, which is going to be 2,000 tons per year. And we're actively looking at locating our first-of-a-kind facility, which is going to be a 25,000 ton per year building block. From that building block, we're going to be looking at scaling that up depending on sites where we're deployed. So you can deploy 4 of those, you can deploy 8 of those. It becomes a mathematical solution, depending on how much power, how much water, and other services you have at site. We think this unique approach allows us to tap into a very large TAM of both permanent sequestration, but also to partner with folks like Carbocrete and others where you could co-locate and you don't necessarily need to make 100,000 or 200,000 ton facilities. There's a huge market developing, but one of the biggest challenges in executing in this market is cost. So when we think about the cost of some of these offtakes, you're going to see that there's a lot of deals announced from Climeworks, Heirloom, and others with Frontier and Microsoft predominantly. A lot of those costs fit into the kind of a $500 to $1,000 a ton category. And these are through the sale of voluntary offtakes. As you think about scaling that up, most of these deals are quite small in volume. So the aggregate dollar figure is quite low, although the unit costs are quite high. One of the largest roadblocks to DAC technology in the scale up is the rapid need for costs down and actively reaching a more normalized marginal cost of abatement that's competitive. Looking at some of the market data, we think that if you drop below $300 a ton, the scale of that market is probably around 5 gigatons of hard-to-abate emissions, where the marginal cost of abatement of DAC is more feasible. If you drop that number to $100 a ton, that becomes 15 gigatons of total addressable market. So as we discussed, it's a massive market. Similarly, DAC poses a unique solution for hard-to-abate sectors like aviation. You would have seen participation from major airlines like Air Canada, Lufthansa Group, Airbus. The reason being is there's large mandates for decarbonization of aviation. SAF, or sustainable aviation fuel, is also a very challenging market that's looking to scale up. And the distributed nature of DAC, not having to have the product adjacent to your airport or adjacent to your hangar, makes a unique solution that allows for you to locate the project where it's most advantaged, has large access to low carbon power, and then utilizing those credits to offset emissions, whereby you otherwise would not be able to have access to low carbon sources. So as we wrap it up, we're located in LA. We have a very large material science and systems engineering team where we're continually advancing what we think is the best in class next generation DAC technology. We are actively looking at our next scale-up project, and we do a lot of collaboration with a lot of schools as well as government agencies, where we look to find unique solutions to scaling one of the biggest challenges that faces us all. Thanks.
So my name is Tim Bushman. I am the Director of Policy and Research at Carbon Removal Canada. We are an independent policy initiative that is focused on the rapid and responsible scale-up of CO2 removal from the atmosphere in order to meet both Canada's climate goals, but also the world's climate goals. I'm going to talk about policy and focus my comments on that, but rather than give you a very broad brush overview of various policy and regulatory drivers that can support the industry, I wanted to focus on what I would call a really rapidly emerging policy tool that various governments are looking at right now, and that is government procurement of carbon removal services. So basically the government at national level or also subnational level acting as a major purchaser of carbon removal in the market. And how that works in effect is that they buy carbon credits from these projects that we just heard about to serve as a major demand pull force in the market. So governments, they procure a lot of things, goods and services. It could be concrete for infrastructure projects. It could be fuels, things of that nature. And so this is kind of an evolution of thought in that regard, where governments aren't necessarily procuring a physical, tangible good or commodity, but rather procuring carbon credits from these projects, in other words, an environmental attribute that they can then use to help meet their own national climate goals. I just want to do a little bit of scene setting to kind of tee up why we think government procurement is so important, and especially at this moment in time for the carbon removal industry. I would just say at a very high level that, you know, historically this industry is very nascent, is very new, so there hasn't been a lot of funding devoted to it as of yet. And much of the funding to date has been towards so-called shorter durability solutions, or some might call nature-based solutions. So things like forestry and soil carbon storage projects. But what we're talking about right now in terms of DAC or even the concrete industry is very, very new, and not a lot of monies have been devoted to it from a carbon removal standpoint to date. We heard earlier there's a major delta between kind of where we're at now globally from a carbon removal capacity standpoint and where we need to get to by mid-century. Estimates vary, but basically we're doing somewhere around 2 billion tons per year of just carbon removal across the board, and that's mostly forestry projects, so kind of beyond natural baseline of carbon drawdown. Of that, there's only about 2 million tons per year that's being done through so-called durable carbon removal through mechanisms like direct air capture. And so we really need to scale up a portfolio of solutions to get anywhere close to these targets that we think we need to hit by mid-century to help meet climate goals. And estimates vary again, but anywhere from like 5 to 10 billion tons per year by mid-century. So we have quite a big delta from where we are today and where we think we need to go. One of the big conundrums with the carbon removal industry is that there's no pre-existing market for carbon removal. There's no market that values the unique kind of societal benefits that stem from removing CO2 from the atmosphere, right? Like most markets, they produce a physical, tangible good that we can sort of buy, trade, and sell within a market. But here you're basically in sort of broad strokes, you're giving money to companies for a carbon credit, which in some sense is just kind of like a digital certificate, if you will, that you can use to retire against your corporate emissions goals or national emissions goals. So it's a bit of an oddity in that sense that you're not necessarily procuring something physical. Now, there are exceptions to that rule. There are some carbon removal methods like electrochemical CO2 separation from seawater. Some of those methods might produce hydrogen, for example, but on the whole, most of these project types aren't producing a physical good. And so it makes creating this market construct around the industry a little more challenging. Just in general, not every policy is likely to support all forms of carbon removal. And so we often talk about on the supply side, we're going to need a host of different technologies, carbon removal methods or project types, right, to get anywhere close to these gargantuan scales that we're talking about. We're also going to need a portfolio approach to sort of policies and demand side drivers to help support this market and get it to scale. And I would just say too, just on that note, that the public sector certainly can't do this alone, nor can the private sector. So we really need to, in earnest, think about that sort of public-private partnership model to get this industry to scale. Real quickly, in terms of carbon markets, they're obviously a really important scaling vector for the industry. You can break it down very simply into two different sort of buckets or tranches. One is the voluntary market, and then one is compliance carbon markets. So the voluntary market, right now, the latest estimates are that carbon dioxide removal projects only comprise somewhere around 3 to 4% of the total market. The vast majority is emissions avoidance or emissions reduction projects. So avoidance could be, paying someone to not cut down a tree somewhere. A reduction credit could be a points or a CCS type of project, but that constitutes the bulk of the market. And there's a very, very small sliver of that market, again, 3 to 4%, that is carbon removal. So we really need to grow that wedge in the market to help this industry scale. There's a lack of buyers in the market, both in absolute terms and then also sectoral representation. So we already talked about Frontier. Microsoft is also kind of a household name in the industry to support these types of projects. But clearly we need a lot more purchasing activity in the private market to complement government efforts. And so we need to kind of grow that demand signal in the voluntary market. There's a lot of uncertainty around how these companies can use carbon credits to meet their corporate targets. There are standard setting bodies like the Science Based Targets Initiative that is actively working towards trying to figure out how to validate companies' climate goals and their approaches to achieving climate goals based in part on using these carbon credits, likely to help meet Scope 3 emissions, but possibly Scope 1 and Scope 2 emissions as well. And so that lack of uncertainty kind of potentially stymies market demand at the moment, and that's something that the industry is grappling with and needs to figure out. You've probably seen no shortage of popular press articles in The Guardian, Bloomberg, and otherwise kind of highlighting reputational risk concerns from buyers sort of in the legacy market, if you will, that have bought carbon credits. And they've been found to be kind of a dubious quality of scientific quality. And so, that has kind of served as kind of hushing the market and stymieing activity a little bit as well, whereby corporations, they want to make sure that these credits are actually leading to sort of valid market outcomes and scientific outcomes. And so that's another problem too, is just grappling with this quality issue within the broader voluntary carbon market. And then I would just say too, that kind of goes hand in hand with, right now there's a patchwork of quality standards, and we really need to hopefully arrive at cross-cutting, sort of universally recognized standards, right, that constitutes what is going to be a quality project from which to procure these carbon credits from. In contrast, compliance carbon markets, they're manifold. There's dozens of these so-called compliance markets globally, many, many dozens. Longer duration CDR or carbon removal is ineligible in most of these markets. If these markets actually do have carbon removal as a qualifying mechanism for corporate emitters to meet their compliance obligations, most of those offsets that are eligible are mostly forestry-based projects. And so we really have to try and expand the scope and aperture of these carbon markets to include the sort of the totality or the portfolio of different methods that we are trying to develop to help scale this industry. That goes hand in hand with lack of standards and protocols for market integration. That obviously has to come first, right? Quality before scale matters. The voluntary market's really important for kind of sussing out technology readiness and helping to develop some of these options. But once we're talking about compliance markets, we really have to have scientific uncertainty constrained to the maximum possible extent. And we need to have technology efficacy, safety, public acceptance, social license. These technologies have to be cost competitive in these markets, which is a problem in large part right now because the prevailing carbon price across a lot of these carbon markets are so low relative to the true cost of doing carbon removal, and in particular durable carbon removal. So we kind of need to see two things in the future. We have to continue to drive down technology costs over time, and we also need to ratchet up the ambition of these carbon compliance carbon markets so that eventually these technologies are more cost competitive. And then just naturally administrative processes, procedures take time for formal market integration. So I kind of look at compliance carbon markets as probably more of a scaling vector for the 2030s and beyond, whereas the voluntary carbon market is really the primary engine of growth for carbon removal at the moment. So long story long, that kind of brings us to the role of procurement. We're really excited about this. So the US Department of Energy came out with their Purchase Pilot Prize last year. And what that is a government mandate to serve as, using the DOE, Department of Energy, to be a customer in the market. So the US Department of Energy allocated $35 million in the latest budget to this procurement program. And it's a first of a kind anywhere in the world, which is really exciting. So the US government positioned itself as a major customer to buy carbon credits from these carbon removal projects in the market. Canada has since followed suit through what they call the low carbon fuel procurement program. So within budget 2024 that was just released in April of this year, they expanded the scope of this long-standing historical program that has traditionally targeted the procurement of low carbon physical fuel supplies. You can think things like sustainable aviation fuel or methanol or ammonia. And they have since expanded the scope of that to include carbon credits from carbon removal projects, which is really exciting. I would just say that governments historically, they've kind of been more associated with like the early stage R&D, like fundamental and applied R&D, and really trying to drive forward those early scientific breakthroughs. But there really is kind of a building consensus, emerging consensus that governments still have a very important role to play kind of across the research, development, demonstration, and deployment spectrum in really helping to, again, from a demonstration and deployment, those last two Ds and kind of the innovation spectrum, really serving as that demand pull force in the market for some of these things that it's developing and helping to develop from a fundamental and applied R&D standpoint. So that's really exciting, and we made this graphic, and sorry, I know everyone had really cool graphics and figures, and my slides do not have that, but in this figure you can see that, we think that public and private procurement programs, for that matter, can really help serve as this like catalyst from a demonstration and deployment standpoint for the market. And I see that I'm running low on time, but just really quickly by way of potential impact, I think these types of programs are indispensable for a number of reasons, regardless of the budgetary amount or the purse that's set aside to do the actual purchasing. We think it can do a number of really beneficial things for the market. So one of which is just establish administrative capacity so that governments in the long term can serve as a major procurement function for this market. You can imagine a world potentially where governments are appending these types of procurement functions to climate targets where they have to meet net zero, and there is no net zero without carbon dioxide removal. You could also imagine governments appending these types of programs to compliance markets, and then a portion of those compliance revenues are then funneled to governments, and governments can use a portion of those revenues to support carbon removal and be that procurement function. There's a host of co-benefits that can come from these projects by way of economic, environmental, social co-benefits. Demand creation is among the most pressing problem in the market right now. There's just a very suppressed demand signal relative to where it needs to be to get to scale quickly. And so we think that most certainly in the immediate term that these types of procurement functions can serve as a really important bridge between voluntary and compliance carbon markets and also other regulatory schemes in the future that can help scale the industry. Funding mobilization, really important to help kind of crowd in and mobilize private sector funding. Knowledge development, of course, like right now we're learning fundamentally. And so these types of programs I think are indispensable because they are coming from a public purchaser and being treated as a public good. You can imagine dispensing that knowledge to the broader industry to promote kind of learning by doing. Market validation, I'll just quickly touch upon that, but these companies, we hear a common quip from a lot of companies that we talk to, and they say that grants, federal grants are great, but customers are better. And you can imagine from a business standpoint, having a government, national or subnational, be a formal customer of yours in the market is quite the marketing tool. And so it's really important from a market validation standpoint that these companies, potentially can have government serve as a major purchaser. They can also take those offtake agreements that they're getting from governments, and they can take that and go raise project financing and so forth, and kind of use that as a means to help attract other sort of financial opportunities. And then obviously just promoting technology readiness. I'm going to just be very, very brief here. I'll just say that we published a report last month on Canada's procurement program, and we came up with what we thought are like 8 core programmatic design considerations that could spell out any sort of public but also private purchasing program, like what the US Department of Energy has, or like what the Government of Canada has, and what the Europeans are looking at doing through their innovation fund. I won't go through these. A lot of these are kind of self-explanatory, and I know I'm out of time, but all to say that it's an art and a science to design these programs, but it is very new coming from the sort of public sector angle. But again, we see these types of programs to be absolutely indispensable to kind of serve as this market demand backfill, at least in the near term, to for the rest of this decade, to help the industry scale before compliance markets, I think, really take hold and come online, and hopefully governments look to embed carbon removal within other sort of regulatory drivers. So I'll stop there. Thank you.
Thank you. Yeah, I'll reflect on the concept of scaling up, which was addressed differently by the previous speakers, and thank you very much for these presentations. I have learned a lot about carbon capture and carbon removal. I'll start with the key concern that we have here as architects and as designers. The climate emergency made us rethink how, not just how we think about climate, but how we visualize nature and how we visualize the different issues, climatic issues related to the climate emergency. The representations of climate traditionally we use this kind of language that is very standard. There's a lack of common visual language to communicate environmental issues, and problems like carbon emission, the massive store of pollution, the rapid degradation of landscapes, biodiversity, and others are represented in simplistic way with traditional cartographic methods or abstract methods, or with scientific or cybernetic images that speak in an abstract way using a top-down aesthetics. This had led, I think, to climate change skepticism and denial. That is why it becomes crucial to rethink first the representational techniques we use to talk about the climatic issues, and these are techniques that for long have shaped the way we look at nature and the way we represent the gravity of climatic problems. As designers, we're better placed to produce alternative accounts of environmental transformations and to represent these intricate environmental issues, not just with statistics, which are a good starting point, but also to think about the complexity of these issues, the multiple scales, gravity, and durations of the climatic issues we are facing. That is how change could become possible, and some designers have been already thinking into this direction. This is the work of Alexandra Aren, who is trying to rethink the traditional layering of rocks, atmosphere, and produces an anamorphosis of this image where we see carbon right in the center. So it's a sharp contrast from the first image we saw where pollution is going up into the atmosphere, but she actually shows us that it's coming back, and we're all trapped in this first in this kind of carbon emission, in the pollution. This new regime of visualization would suggest that we are all part of this, that we all live within nature and interact with it. Or as Isabel Stengers will say, we feel the intrusions of Gaia, and we weave a web of connections that might hurt or repair the balance. That's another attempt to visualize these connections by Design Earth. So instead of acting against climate change in a militant way, as architects, we're better placed to act from within, rethinking the connections and the relationships with nature, raising awareness, and also crafting solutions. And these summits are very much about those solutions. To better grasp the solutions, we need to understand what happens in the laboratories of architects, engineers, scientists, and entrepreneurs, and we have already had a glimpse to those laboratories in the previous talks. We need to ask ourselves what kind of material practices and experimental tactics are at stake in those laboratories as we face the climatic challenges, the challenges of the new climatic regime, as Bruno Latour would say. What materials should be mobilized to enable a construction based on low carbon and carbon removal, and how will this alter the wider ecology of professional architectural and constructional industries? Trying to come to terms with the legacy of modernism that led to the extensive use of carbon-intensive materials based on extractivist methods, we all realize today in our practice, but also in pedagogical settings, that the materials that we traditionally use have all become matters of concern that have harmful effects on our health and well-being, but also impact ecological balance and communities at a global scale. And I think that is also what the Natural Materials Laboratory, directed by Lola here at the GSAP, is trying to experiment with this new materials to find alternatives. So if we think about the traditional materials that we inherited from modernity, we can take asbestos or reinforced autoclaved aerated concrete or even wood and sand. They're all problematic, and they're far from being stable technical or material resources. They're all highly controversial and contested, and they have become objects of preoccupation. That is why it becomes impossible to take, it becomes impossible for us in our practice and in educational settings to take materials from the shelf. And we feel the urgency to fundamentally rethink and change our working methods, relying on novel tools to explore new possibilities, but also experimenting, as David has demonstrated, with new materials, with biogenic and geogenic materials, shifting also local and towards local and site-specific solutions, rethinking cycles of expertise and technologies. As illustrated by David, renewable plant and earth materials with circular life cycles might provide an answer. And in this process, our architects are not just in control any longer, but architects become active agents in the cycles of material experimentation. This active role can empower us also to rethink the process of an implementation of an invention, or what we call here scale up. And we have seen a different understanding of scaling up in the previous presentations, where we had a glimpse of how scaling up is understood as a way of implementing an invention. When we think about scaling up, traditionally scaling up is understood as the scaling up of an invention from the lab of a scientist, an architect, or an engineer to a kind of societal level, increasing the size or the importance of research, or the growth of a company, the visibility, or the scale of the market, as Tim has mentioned. Up, in a way, points to society. Up points to this kind of magical move from the lab to the society. And there's an expectation that society with a capital S is capable of influencing, directing, and even shaping the implementation of this invention. Yet the notion of up with capital U, up and out of the lab, implies diffusing an invention. And as such, and it's typically the diffusion of an invention that is crafted by human creators. And this concept as such is limited and, I would say, human-centric, this diffusion model, we could call it after Latour. The assumption that a society forms that ideal milieu in which ideas can travel, can be developed and diffused is losing currency. Why? Because we assume that society is out there, it's structured, is made out of social groups, and they all have their interests, and they will just react to our invention in one or another way. They'll resist or accept it, or ignore the invention. And by doing so, we just maintain the distinction between science, technology, and design on the one hand, and all of them sitting in their laps, and society on the other. And this distinction is not useful. This kind of purification can only lead to misleading interpretations, such as social constructivism or technological deterministic interpretations. However, we all know that we don't know what society is made of, just as we don't know what nature consists of. And in the process of invention and experimentation, as we have seen with the case of carbicrete and the low-carbon concrete, and with David's example as well, both designers and engineers create a world in which to work. They don't just export an invention outside. They create, they craft this world. So we are in the regime of the translations. They re-articulate and they try out new alliances, new associations. They displace interests, they negotiate facts, they regroup the forces, they reshuffle political alliances and recruit supporters. And this process is much more complex than the simple scaling up movement. It's a complex process of translation which involves multiple participants, which constantly modify and displace their interest and translate their interest. I was actually very happy to see in Tim's diagram diffusion appearing at the very end of the diagram as this kind of linear process of step-by-step export of the idea from the laboratory, from the hardcore research stage to the final stage when the idea is diffused to society. But in reality, if we look at the practices of engineers, scientists, and designers, what happens is much more complex. We all work on building a network, carefully crafting groups and aggregates of supporters, designing a world where our invention could travel, and thinking carefully about how to prolong the work we have started, thinking about the other actors, but also materials, protocols, regulations, and prototypes. And this implies a relational thinking from the start, and this implies thinking carefully about the stronger and the weaker relations, and in this process, we mobilize heterogeneous entities that operate at different scales. And I think it was very interesting also to hear from Aidan that when you scale up, you also descale according to local sensitivity and local solutions. That's very interesting. So you're already in this kind of translational model of negotiating the specificity of these inventions and scaling up and down, descaling. And we know it from design. A new building also emerges through many different scales, and emerges as scales are shifted, and it implies seeing simultaneously in different scales through a variety of presentational states. So the design process is very far from being an evolutionary kind of progressive step-by-step venture, but we have scaling up and down, which does not imply successive moves, but parallel moves, parallel states, each containing the other and referring to the other. The scaling up never goes up, as the chronologically kind of successive move of an evolutionary design process, but rather runs back and forth, scaling, descaling, scaling up and down, back and forth in a circus, building this kind of community of supporters. And that is what allows designers, engineers, scientists to produce things, but also to simultaneously craft and produce the social context for those things. Just like engineers and entrepreneurs produce the products and the markets, and we have seen this very carefully developed in Tim's presentation, where the market is also unpredictable and has to be carefully crafted, and the policies are also kind of diverse and have to be carefully crafted and adjusted according to these translations to the different kind of actors that participate in the scaling up and down. In conclusion, there's no framing. This was the design process. In conclusion, there's no framing, no context or society out there ready for us to perform our brave scaling up move. Each time we design, everything is to be redesigned and rethought about both the content and the context. The materials, protocols, tactics, and solutions that we have heard about here today and that will be developed in the future will help us to reduce carbon emissions. They will help us to develop new typologies, not just for carbon capture, but for storing. And there's this new typology emerging, the long-term typology storage that we talk about, not just about carbon, but about nuclear waste, but also positive storage typologies, the museum reserves, the seed banks. There's this thinking about long-term storage that is there, and this thinking will also help us to craft new social links connecting humans, nature, and technology in a radically different way. That is how also architectural design can become a powerful tool for re-articulating and rethinking the cosmopolitical order. Thank you.
Thank you, everyone, so much for everyone's take and information and efforts that are so uniquely different. And I was asked to prepare a question in 23 degrees Celsius November that started with thinking about what are the actioning terminologies towards climate, so we can be looking at resilience, looking at how communities adapt to challenges of climate. We can look at grief towards a changing world and a lot of death that is around us and that is anticipating. Compassionate towards previous generations and future generations that will need to endure. Escapism, looking at the next colonies on the moon and 3D printing using moon sand or moon geology, and we can fight against carbon or act against, as Albina said, and we can strategize solutions, which is somehow what we are looking here with the 3 lectures by Mehrdad and Yuri and Aydin and Timothy. That is kind of the design/engineering/STEM or technoscience approach to tackling and the terminology around carbon actioning, which is basically tackling the problem with the same tools and mindsets that created or provoked or led to the crisis today. So what I'm really curious, especially with Aydin and maybe Mehrdad and Yuri and somewhat with Timothy too, is we're not investors in your technology, or most of us we're not gonna be investing in your technology, or we're not your climates. I'm really curious for you to unveil the carbon accounting, the full cycle carbon accounting. For instance, the production of steel slag. What is the transportation requirements? What is the production of steel slag requires? And the dependence on steel for the steel slag, what does that mean? So you mentioned 250 million carbon storage given the use of all the steel slag in the world. What is this codependency with the existing mechanisms of industry of steel, which is a carbon emitting industry by its own? And what are the mechanisms of making the chambers that take the CO2 into the new concrete, right? So you save carbon and you suck carbon from the air, but of course there is so much carbon required for the technology, and I'm really curious about that. And for the units and the modules, what is the space, what is the land measurement that is required? What about labor in these technologies? And of course, there's so many increasingly flawed and biased notions in carbon accounting, and I really am curious to hear kind of the back of the stage, or also kind of the criticalities towards your own technologies, just because, right, the conversation around also the challenges.
Yeah, thank you. I have one comment and one question. The comment is about the question of sickness. I think you are talking about to have a big quantity of wood to have the storage of CO2 inside the wood or inside the concrete. So there is a change between the 20th century and the 21st century. During the 20th century, we wanted to reduce the thickness of things, to have transparency, to have lightness, and it's also a cause of the global warming because the absence of thermal insulation and force us to consume a lot of energy for warming the building. And now we are going into a moment when we can increase the thickness of material of the building, and maybe it can be also helpful for increasing thermal inertia and to try to get the coldness of the night for giving it during the day, or the coldness of the winter to have it during the summer. So I like this idea that there is a shift from the lightness to the heaviness of the architecture, and this is something that we have to develop in the field of architecture. And my question is about carbon capture. I don't understand really why we are capturing the CO2 and then we have to do something with the CO2. Why we cannot do like the plant with photosynthesis to capture the CO2, keep the carbon somewhere, and then re-emitting the oxygen somewhere else. So why we don't have this technical possibility as a plant for doing that in an industrial way?
Thank you. It's I came into this prepared to discuss scale and was going to, and I still will bring it up, but, and this is just quoted here, inside a business school protocol, to scale means to increase revenue or profits at a rate that exceeds investments in resources. So we know that from, from a century of that type of mass production. But what I would get at today is kind of two questions. One is that, in my experience working around scale in an unnamed car company on the West Coast, is that the disruptive product today scales because it actually scales in multiple dimensions. So the electric car is electric. It also changes the center of gravity. It's electromagnetic from computers to engines to the network, and et cetera. So it no longer scales as one product, your iPhone, et cetera. And so a kind of hypothesis that those products that can scale in multiple vectors attract capital. This is not a new theory, at rates that exceed. So the building industry is troublesome that way, I think, or has resisted scale in that regard. But not to challenge anybody here in that regard per se, but I want to put out a few numbers. In 2023, 4 banks failed in the US. Silicon Valley Bank first. That total failures were measured by the FDIC, $549 billion. They were about 80% of the 500 plus banks that failed in 07. So the idea that our economy that we're scaling into is stable is a huge question. In 1996, US housing was worth $9 trillion. In 07, 24, in 13, 18, and 17, back to 27. In 24, it's worth 50 trillion. Bloomberg last year estimated that it might take 79 trillion to get the world to net zero. So it's like 1.5 times the housing stock. The housing stock was largely built since 1950. The number is shocking, but not. If you went down that central banks in the world, in 2002, central banks in the world were holding about $2.5 trillion. Today, the top 7 central banks are holding about 33 trillion. They've mopped it up from market failures, housing, COVID, recessions, et cetera. So I bring all that up to say that scaling is so interesting a question to bring into an architecture school as a business protocol. You mentioned you have competitors. I don't remember Zaha Hadid saying my competitor when she spoke here, but it's true. In a world of scaling, you have competitors, and there are technological valleys of death and market valleys of death, which are mentioned. So I guess a question I would have is, it seems like an incredibly difficult time. Like if we imagine automation of labor wiping out X, what is the economy we're scaling into? And maybe we have to begin to imagine that development is a different type of asset than one that has been measured by real estate taxation or labor even, that it's more akin to some larger measure of biodiversity, something, and David opened the night, I think very beautifully by saying, how do we get an imagination to said numbers? So I would just like to say that maybe what we imagine is an achievable scale is an exceedingly difficult question at this moment in history. And thus this conversation is all the more pivotal in a school like ours. Thank you.
Thanks to all three of you. This is a lot. Let's see where we can get started here. Maybe let's start with Philip's question about the sort of technological question about, why can't we not do like plants?
Yeah, happy to take that. And maybe I'll combine two of the answers. One about the life cycle analysis of how we measure this, as well as what do we do with the CO2. So your analogy is a good analogy, and we do something similar to that. That purge cycle does get rid of most of the air. The issue with CO2 today is, what do you do with it? So when we have this pure CO2 source, there are value streams that we talk about. Today, CO2 utilization is primarily in enhanced oil recovery, where they inject it in a reservoir, increases the mobility of the oil, and they produce it. It happens a lot in West Texas. It's been happening for 30 years. The rest of the sector of utilization is primarily urea for fertilizer, as well as the growing sector of concrete. I think carbon to value is important, and I think sustainable aviation fuel, adding hydrogen and making it a hydrocarbon, basically accelerating what happened in the earth, is a great pathway. Those are also emerging technologies. So we at Carbon Capture have a partnership with a company called 12, who is a sustainable aviation fuel producer. And so we are exploring all of those power to liquids plays. The second part of the question, and I didn't catch your name, so I apologize, around life cycle analysis. So when we capture and calculate the net carbon removed from the atmosphere, we factor the carbon emissions of the steel that we use. We factor all of the emissions of the components, the trucking to get it to site. We amortize that across the life of the facility. We also include the carbon intensity of the power that we consume. And when we calculate all of that through a protocol, we get to a net carbon removed on a life cycle basis, and that's how we generate credits to maintain the highest integrity. So we can mathematically and quantitatively demonstrate that we have actually removed a net amount of carbon. I think that sums it up.
Thank you. Do you also want to respond? Yes.
In terms of the life cycle assessment, I would just echo exactly what you said. We've done the same thing, and we're compelled to do the same thing if we're going to be active on the carbon markets. In terms of our dependence on steel, you're 100% right. Our feedstock comes from the steel industry. We don't believe that steel is going anywhere. That said, steel is getting greener, and there's a massive shift to electric arc furnace production of steel, which actually is a benefit for us. It generates more of the kind of slag that we can use as our feedstock.
Thanks. And maybe we can, Tim, do you want to pick take on Michael's question? Maybe on this, or you wanted to respond to this?
Sure, yeah. I was just going to reflect on, I think, all the questions real quick. But yeah, the life cycle assessment question, really important. I think that just underpins like whether or not you have a net negative project, right? So LCAs are just absolutely indispensable component of proving out your project. there's emerging industry best practices by way of how LCA should be carried out. We typically say like full cradle to grave life cycle assessments are really looking at the totality of the project, right, from upstream to midstream to downstream, if you will. Take into account all different types of greenhouse gases, so CO2 and non-CO2 greenhouse gases, right, and then making sure that at the end of the day, it's kind of like doing the climate math and making sure that you truly do have accounting for all these different factors that go into it, whether it's energy requirements and so forth, that you truly do have a net negative project. So really, really important component of that defining quality in a project in the market. On the question of plants versus other storage mechanisms, I would just say like plants are really important, right? Photosynthesis is a beautiful, amazing thing. We need more forestry projects. We need to hopefully figure out how to make soil carbon storage more recalcitrant. So that's really, really important. I think there are reasons to want to branch out beyond that. One is just durability considerations, right? So if you think about carbon storage, you can kind of think about it in two broad buckets. It can be biological or non-biological, or biotic and abiotic. The biological, really important from the standpoint of ecosystem services and so forth, but it is vulnerable to physical reversal events, right? So you can imagine a stand of trees, right? And if it succumbs to a wildfire or succumbs to pest infestation, right, that carbon can be re-released into the atmosphere. So those are concerns. There's also issues with like, if we're talking about replanting trees at like northern latitudes and some of the boreal forests, that could actually negatively impact the reflectivity of the Earth, the Earth's albedo. And so from a net warming standpoint, that actually could be detrimental from a global warming climate change standpoint. So in effect, there's a right way and a wrong way, and a right place and a wrong place to plant trees. And so I would just kind of mention that as another means to think about differentiating, like plants really important, trees really important, but we need to think about all these edge cases, if you will. Then I would just say too that there's a concept called kind of like for like compensation. So a lot of these companies that we're talking about, right, they're buying these carbon credits off of these carbon removal projects, and they're making what's called a compensation claim. So they're compensating for fossil-based CO2 emissions that they can't otherwise eliminate from scope 1, scope 2, scope 3 activities, right? And that fossil CO2 is going to persist in the atmosphere for thousands of years, for millennia. And so we need to make sure that if they're making a compensation claim by buying a carbon credit from a particular project, that the duration of that carbon storage is going to equate with how long the atmospheric residence time of that CO2, right, from fossil fuel combustion. And so that's kind of like this like for like principle. Now there's ways around it, right? You can imagine overbuying carbon credits from like the shorter duration projects. So you could overbuy credits from like forestry projects and in an additive sense, try and marry that to the atmospheric residence time of CO2 from fossil-based emissions. But all to say, like, matching that durability, right, in terms of when we're combusting fossil fuels, I think is really important and is kind of compels us to think about, you know, plants and biology-based sequestration, but also sort of the abiotic sequestration as well.
Thanks, Tim. David, yes, I was going to come to you.
Thanks everyone for all the great presentations and also responses and questions. I just want to offer a quick thought, you know, a little bit trying to bridge some of the more technological and even business side to, you know, what we do here at the school. And, you know, this is a loose kind of early argument, but I think it would be worth discussing and even debating about how we might be in a really new paradigm without realizing it and without acting like it. So in other words, you know, I'll try to connect a couple of dots here, but you know, the climate emergency, I was trying to show that very briefly with these graphs of blue and red, if you remember that. I mean, we're literally beyond any historical precedent, and we're hitting tipping points that are irreversible. You know, we're gonna have irreversible change, and things are getting pretty bad, not to be super negative, but so what do we do about that? I mean, I think it means, like, just to talk about a couple of things, for example, a living plant, like biomimicry, that's great for the old paradigm. You know, the old paradigm is like, we have the carbon cycle, we have this natural loop of growth and decay and regrowth. A plant is zero because it absorbs carbon, but then it dies and it emits the carbon. So in the new paradigm, we can't be zero. Zero isn't good enough. You know, it could have been if we acted, you know, 20 years ago, 50 years ago, but we didn't. So that's what's animating me in this. So we need new tools, new frameworks to think about the new paradigm. I mean, if you follow all my assumptions here, which you may not, but so we need new terms. We need a term like carbon negative. I don't love that term, but we need this idea of we need to have something that we do that absorbs more carbon than it emits. And we can try to utilize that, and we can try to make building materials like that, and we can try to promote policies that do that. So we obviously need life cycle to measure that. So we need to get really good at that, and we need to critique life cycle, but practice it in a better way and not just critique it. We need new forms of imagination for new building types, and I like what you were talking about, Albena, and what you were mentioning, Philippe, about the thickness of the wall. We can imagine this new building type that's not necessarily about transparency, at least not literal transparency and lightness. It's about thickness and heaviness. And I think we also need a new paradigm for speed. Like, we can't debate too much because we have to act, or we have to act and then debate at the same time. And I think that might be really unique for what we've always done. And I just think that's critical. And then finally, we need a plan. If we don't like the plan of the new carbon removal industry, then we need to articulate a better alternative. Or we need to get involved in the discussion between nature-based and technology-based. But we need that plan to also add up. We need it to scale. We need to, if we're not going to, if we find a critique with the idea that we need to remove 40 gigatons and, reduce by 40 gigatons and remove 10 gigatons, we may not like that particular framework, but if we don't, then we need to articulate something else that's going to avoid all of this catastrophe. So, I mean, sorry, I don't mean to be preachy here or anything, but that is what is like keeping me up at night, literally. And I think this school and architects could be incredible players in this, but what it may require is a little bit of compromise, but like a lot of situations, if you want to get something done, you may have to compromise.
Thanks, David. Are there any questions from the audience? Can I collect? Okay, I don't know if Albena wanted to respond to anything, or should
maybe I'll just add multiscalarity is an important dimension to this model, and connected to Michael's comment about the importance to scale up in multiple dimensions and in multiple settings. And we have lots of historical examples from history of technology. For instance, if we think about the bicycle, and it was all about its end of 19th century, and the predecessors of the bicycle, the first bicycles, were developed in the span of 15 years, perhaps, or 17 years, all at the same time. It was kind of a very intensive process of experimentation, different prototypes. And if we look back at this process as historians, we see an evolution. We see kind of all this kind of different prototypes, one evolving into another. But then if we look closely at what happened, and perhaps it was a similar moment, but for end of 19th century moment of invention. All these prototypes, they existed at the same time. They just targeted different users, and they were developed at different scales. Yeah, this kind of big dinosaur predecessor of the bicycle that we have with the big wheel, the penny farthing bicycle with the asymmetrical wheels that we only see in the science and technology museums. This was the very first bike, and through all the problems and trials, many different prototypes were developed for different user groups, experimented, very much like what we see in engineering testing, and they all existed at the same time. And speed was important, testing was important, the mobilization of different groups with their interests, the protests of the anti-cyclist movement, and we can go on and on with this, but at the end, there was the safety bicycle, and this was the stabilization of this long process of invention. So if we look at this, we see centuries of invention, but it's actually a very intensive moment of experimentation, of scaling up at multiple scales and in multiple settings and dimensions so that we achieve a prototype that works for everyone. And this is the safety bicycle, which we have today, the contemporary bicycle. So this multiscalarity is perhaps something I could add to David's model.